We continue our series on probability. This time we want to assign numbers to events. We do that by establishing the axioms of probability. We'll spend a good part of this video working through exercises to build a solid understanding of these axioms, so make sure to watch until the end. Short recap. In the previous video, we defined the sample space, which is the set of all possible outcomes. We also defined events as subsets of that space. So far, probability has been about structure, about sets. Now we ask the next natural question. How do we assign numbers to these sets in a way that makes sense? We assign numbers to sets by using the probability function. It's a function because it's a mapping from an input to an output. The probability function P takes an event, which is the set of outcomes, as input, and outputs a number between 0 and 1. This is how every event gets assigned a number, but not every assignment of numbers is allowed. To make probability consistent, we impose rules. These rules are called axioms. An axiom is a statement or proposition which is regarded as being established, accepted, or self-evidently true. The standard axioms of probability were introduced by Russian mathematician Andrei Kologorov in 1933. The first axiom of probability goes, for any event A, the probability of A is greater than or equal to 0, which means it's non-negative. At first glance, this axiom feels almost too obvious, but that's exactly the point. The smallest value a probability can take is 0. When P of A is 0, the event A is considered impossible, unlikely that it never occurs in practice. In mathematical terms, such an event corresponds to the empty set. Probability is meant to describe likelihood. A negative likelihood simply doesn't make sense. You cannot be less than impossible. This axiom lays the foundation for everything that follows. It ensures that probability behaves like a sensible measure of size or weight assigned to events. The second axiom of probability. The probability of the entire sample space is equal to 1. In symbols, P of omega is equal to 1. The sample space represents everything that could possibly happen. The probability of something happening is 100% or simply 1. This represents absolute certainty in probability since an outcome of a finished random experiment must happen. For example, if you toss a coin, you will get a result, and any of the outcomes belong to the sample space. Think of probability as dividing up a fixed amount of certainty. That total amount is 1. This is what is meant by normalization. Every event gets a share of it, but the whole system always adds up to the same total. This axiom gives probability a natural scale. 0 means impossible, 1 means guaranteed, and everything else lies somewhere in between. Without this normalization, probabilities wouldn't be comparable or meaningful. Now to the third axiom of probability. If two events are disjoint, meaning they don't overlap, and therefore cannot happen at the same time, then the probability that either A or B occurs is the sum of their probabilities. These two events are also called mutually exclusive, meaning they share no outcomes. Then counting both together is just a matter of adding their probabilities. Nothing gets counted twice. This mirrors what happens with sets. Union combines sets, additivity combines probabilities. This axiom only works because events are sets. For example, when rolling a die, the event rolling a 1, the event rolling a 3, and the event rolling a 5 cannot all happen at once. So the probability of rolling an odd number, in this case either 1, 3, or 5, is just the sum of each individual probabilities. Remember that an event is a set. Therefore, an event can contain one element. This means that a single outcome can be represented as an event with the outcome itself as the only element, and therefore we can assign it a probability value using the probability function. Like we do here, this outcome 1 is represented as an event because it is inside the set, and we map that using the probability function. This axiom turns probability into a consistent measuring system. It ensures that probabilities combine in a predictable way, just like lengths or areas do. Together, these three axioms form the foundation of probability theory. Everything else, conditional probability, randomness, even machine learning, rest on these simple ideas. The three axioms of probability lead to the following consequences. First one, the probability of the empty set is 0. This is caused by the first axiom of non-negativity, which we talked about in the previous slide. Next, the probability of a complement. P of A complement is 1 minus P of A. And this is because A complement and A, when added together, become the sample space, and the probability of the sample space is 1. And therefore, with algebra, this equation holds true. Let's go to the next one. If one event is contained inside another, in this case A is a subset of B, then probability of A is less than equal to probability of B, with the event A being the smaller set. And to the last one, when events overlap, we should correct for double counting. In this case, when A and B overlaps, then the probability of A union B equals probability A plus probability of B. This is from the third axiom. But since we have to correct, we should subtract that by the probability of A intersect B. Subtracting by this amount ensures that we do not double count. Now notice that even though A and B do not overlap, this equation still holds true because P of A intersect B becomes 0, and this is just the third axiom. This whole equation is also called the inclusion-exclusion principle. I've got a few exercises coming your way. Our random experiment is flipping a coin, which you are used to by now, with the sample space of heads and tails. Now your task is to assign true or false to the following statements using the axioms that I've provided here. Take the time to pause and try it yourself. Let's go to the first statement. Here probability of heads is 0.6 and probability of tails is 0.6. Now when you add them up you get the sample space, but 0.6 added together equals 1.2. So this does not satisfy axiom 2, therefore this statement is false. If the idea is to model a fair coin, then both of these probabilities should be 0.5, adding to 1. Next statement, probability of heads is 0. Now this is a bit nuanced because it doesn't go against any of the three axioms. But for practical reasons, when we define a sample space, all of the outcomes here are possible outcomes, and therefore in this case heads is always possible. We cannot assign it to 0, otherwise it would be impossible, making this statement false. This will be more involved when we talk about continuous sample spaces. And the third statement, probability of heads is 0.1 and probability of tails is 0.9. This is true because summing them up, leading to the sample space, the probability becomes 1. This can be used to model an unfair coin where the tails part is weighted, leading to 90% of the coin tosses to tails. Let's go further. Here we define the event A as the event with outcome heads and B as the event with outcome tails. Try to calculate the following: probability of A union B and probability of A intersect B. Pause the video and try it yourself. Let's do the first one, probability of A union B. If you combine these two events, you get the sample space, therefore making this probability 1. Next, probability of A intersect B. There are no outcomes which exist in both events. Therefore, the intersection is the empty set, which is the impossible event. Therefore, the probability is 0. Another way to express A union B is the probability that either heads or tails will land. And that is certain because when you flip a coin, one of them must happen. As for A intersect B, it can be interpreted as the event where both heads and tails land. This is impossible because a coin flip can only land one outcome. Let's do a variation where this time we flip the coin twice, resulting in the sample space of heads heads, heads tails, tails heads, and tails tails. Here I've assigned all of the following values to each individual outcomes as events. These numbers are the results of the coin being an unfair coin, which is slightly favored towards heads. Here we define the event X, where at least one heads land, and the event Y, where at least one tails land. And your task is to calculate the following probability values. So pause the video and give it a try. Right, let's do it. Here I've got the Venn diagram with the individual outcomes and its probability values. First, we need to define the event X. So the event X here is where we land at least one heads, and that consists of the outcomes heads heads, heads tails, and tails heads, as shown with the blue boundary. We don't include tails tails because it does not contain a heads. The same for event Y, where at least one tails land. That consists of these three outcomes except for heads heads. So we're ready to calculate the probability values. Let's start with calculating the probability of event X, where at least one heads land. And we do that by simply adding each of the individual outcome probabilities. 0.36 plus 0.24 plus 0.24, and we get 0.84. For event Y, same. We add 0.24, 0.24, and 0.16, and we get 0.64. Now for probability of X union Y, well, this results in the sample space, and the probability of the sample space is equal to 1. Because if you add all of these together, you should get a 1. Now for probability of X intersect Y, so the intersection of these events, well, that includes tails heads and heads tails. Adding them together, we get 0.48. One thing to note here, if you remember from the previous slide, we had the inclusion-exclusion principle. Here, since X and Y overlap, we need to subtract with the intersection. Try to plug in the numbers and verify it yourself. I've got one more for you, and we cannot do an exercise without rolling a die. So that's our random experiment with a sample space of rolling a 1 to 6. We define the following events, where event A is rolling an odd number, event B rolling an even number, and event C rolling a prime number. Your task is to calculate the following probabilities. Note that I did not assign any probability values to these outcomes, but use this fair die as a hint. So, try it yourself and pause the video. Alright, let's do it together. Because we have a fair die, each of these individual outcomes have the same likelihood, and therefore we need to assign them the same probability value. Since we have 6 different possible outcomes, then each outcome will be assigned 1 over 6 in order to fulfill the second axiom, where the probability of the sample space which is the set that includes all of these individual outcomes, amount to 1. Here is the normalization part of probability. Next, we want to define the events A, B, and C. So for event A, rolling an odd number consists of 1, 3, and 5. Event B, rolling an even number consists of 2, 4, and 6. And event C, rolling a prime number, consists of 2, 3, and 5. Now we have everything set to calculate the following probability values. Probability of A, where A is rolling an odd number. So the event A consists of rolling a 1, 3, and a 5. And adding these probability values together results in 3, 6, or in other words, a half. Next, probability of B, rolling an even number. The event B consists rolling 2, a 4, and a 6, so that's 3 elements, which makes the probability also a half. And probability of C, rolling a prime number, 2, 3, and 5, that's also 3 elements out of 6, so the answer is also a half. Now moving on to probability of A intersect C. This event consists of the outcomes that are both odd and prime. And the outcomes which are odd and prime are 3 and 5. So that's 2 outcomes out of 6, and if you add them up, you get 2 over 6, or 1/3. Now let's combine them. The probability of A union C. So we combine the events A and C, which we will get these outcomes. So 4 outcomes out of 6 makes it 2/3. And lastly, the probability of B union C. So we are combining event B, rolling an even number, and event C, rolling a prime number, where the union consists of 2, 3, 4, 5, and 6. So we have 5 outcomes out of 6, which makes it 5 over 6. And a bonus one for you. Remember the inclusion-exclusion principle? Here the events A and C overlap, and therefore when performing additivity, we have to subtract by the overlap. If you plug the numbers in, you should get the correct results. Notice that in this exercise, we assigned equal probability to each possible outcomes. This sets up a smooth transition to the next video on classical probability and counting. At this point, we've laid down the entire foundation of probability. At its core, probability is built on just 3 simple ideas. First, probabilities are never negative. They measure likelihood, and likelihood cannot be less than 0. Second, all possible outcomes together have probability of 1. Something must happen, and probability is always measured relative to this fixed total. And the third, when events do not overlap, their probabilities add. This ensures probability behaves consistently when we combine events. These axioms are not results we prove, they are results we accept. Once we do, they give probability a precise and reliable structure. Everything else in probability theory follows from these 3 axioms. They form a complete foundation for reasoning clearly about uncertainty.